we'll do a really quick review because I don't want to spend too much time on it. So for A, since you can look at your quiz, for A, these are two parallel resistors. Voltage divider equation, no. So for A is overall resistance. So VO over our total. So this is our total here for the parallel resistance equals VI over R1 plus our total, right? So VO over, or just move this one to here. So VO equals VI times our total over R1 plus our total, and that's it, 30 points. So B, it's a replace that with our total and derive the voltage divider equation. So the voltage divider equation, how did we derive it at the very beginning? Voltage divider equation. So it was VO equals I, if you assume this is I times our total. VI equals I times our total plus R1. So left divided by left, right divided by right. So VO over VI equals I times our total over I times R1 plus our total. All right, and then cancel. So VO. Wait, am I doing the same thing for the two? What I'm doing here? Oh, yeah, this was wrong. Let me redo it pretty soon. Okay, so this is done. So the B number D, so B is correct. For A is to find out equivalent resistance. So this was wrong. So VO over our total equals, because this is the overall I and being split into two branches. So it should be VO over the voltage across this guy over R2 is a branch current here plus VO over R3. Right, and then cancel VO here. Right, so you can find out our total equals 1 over okay, so that's the solution. So C, I didn't ask you to derive it, so you can use the conclusion from the, if you want to derive the conclusion for the current divider, you can do that, but here we're not asking to derive it, just represent the current flows through here and here using VI, R1, and R2, or R2 and R3, and R1. So you know that I2 equals I times, that's a conclusion for current divider, right? So I2 is the I here. I2 equals I times R3 over R2 plus R3. Here's the conclusion. The conclusion can be found in the notes from class 1, from lecture 1. I3 is I times R2 over R2 plus R3. Okay. So what is I? Yeah. And since I'm asking you to use VI, R1, R2, R3, only VI, R1, R2, R3, right? So you can just replace I with VI divided by something. So in that case, I2 equals I, which is VI over what? R1 plus R total, is that correct? Okay, so the overall I times R3 over R2 plus R3. And I3 equals VI over R1 plus R total times R2 over R2 plus R3. And then replace, you know, our total is this, okay? And just plug this in here, then you're done for all the three problems. Just replace our total because it's asking you to only use VI R1, R2, R3, right? But not anything else. Yeah, take a final look at it. I'm gonna scan it and post it to the website. Or something related to the homework assignments, which is DACs. How do you characterize DACs? So if you look at the textbook, it's page 941 on the textbook, Dr. Baker's book. And starting from here, so that's one of the parameters you want to characterize for DACs. So differential nonlinearity, or DNL for short. So it's overwhelming to read everything, but just remember that DNL is what? Nonlinearity, yes, but intuitively it is an increment. How do you remember it? Because there are a couple of very similar concepts. So it's an increment compared to LSB. I know there are some grammar issues here, but that's the shortest sentence you can remember to differentiate DNL and NL later. Okay, so what is NL? That's the actual value compared to the ideal value. And we're going to look at the curves to understand it. Just reading these sentences do not make any sense. It has grammar issues here as well. So for example, you take a look at this curve, okay? X and Y. So for DAC, X, remember the DAC, the DAC, is digital to analog converter. So it converts digital signal to analog signals, right? It's a 3-bit DAC, so that makes sense. So the inputs are digital numbers, and these are the outputs, analog voltages. So whenever this jumps, so if the input is 0, you're expecting 0, no problem. Okay, but whenever it jumps to 0, 1, you're expecting a 1 LSB output from the analog voltage. Just keep moving, keep moving. So like what we said here, DNL is an increment, or it's actually incorrect increment compared to LSB. So you are comparing the increment to the 1 LSB. 1 LSB, keep in mind. It's how to do the calculation. It's going to be on the homework assignment and the quiz. So it's comparing the increment for each step to 1 LSB. How? Let's take a look at it. That's an increment. Is that 1 LSB? Yes, no problem here. See, that's one step up, which is 1 LSB. Jump to here, there's another increment. It's still 1 LSB increment. What about this one? So DAC is not doing a great job. So you can label that DNL, keep in mind, DNL is a differential nonlinearity, right? DNL, and you label it as DNL3, because this is 3 here, right? 0, 1, 1 is 3. DNL3 is the increment compared to 1 LSB. So the increment here is 1.5 LSB. It's designed to be that, okay? You're asking me, how do you know that? It's just in the textbook, they designed this one to be 1 LSB increment, a 1.5 LSB increment. So the DNL3 becomes 1.5 LSB minus 1 LSB. It's going to be 0.5 LSB, which is a DNL3. So you'll know that the non-linear, differential non-linearity at 3, okay, is 0.5 LSB. So when you write it down, you denote it as DNL3 equals 0.5 LSB. And that's it. Does that make sense?
Yeah.
What's the problem here?
Why don't they all have the same jump? I'm confused why they don't go up the same amount?
Yeah, so the components are not, the components are not really accurate. If you look at the resistors, manufacturers, what's that called? The ratings or something? So there's accuracy at the very bottom, at the very end, right? It can be 0.5%, 0.05%. They're not really, you cannot find a perfect component ever, okay? So what about this one? What about DNL what? 4 is what? See, 0.5 ideal height. So which means the height here is 0.5 LSB. All right, compared to 1 LSB always for DNLs, you just look at the steps, the step size or the increments, and just minus 1 LSB. That's it. So don't read all the things here. It's okay. How to find DNLs? Just find out the increment minus 1 LSB. Make sense? Okay.
So the increment for that 4 would be negative?
So
or the DNL?
So DNL 4 equals 0.5 minus 1 LSB, which is negative 0.5 LSB for DNL 4. DNL 5, you see, it's already what I told you, right? It's 0.5 LSB. So you're going to use 0.5 LSB minus 1 LSB. You're getting negative 0.75 LSB. That's for DNL what? 5. Okay, what about DNL 6? It's a very big step. 0.75. What? Yes. What about this one? 0. It's 1 LSB minus 1 LSB is 0. So DNL 7 is 0. That's it.
Where do we apply the DNL? What is the DNL?
Which one?
Oh, like when you calculate it, is that just to tell you the LSB?
For each one. You can plot it. Now, let's talk about integral nonlinearity for DACs. Remember what I told you here? NLs, integral nonlinearities, is the actual value compared to the ideal value. So you are not looking at the increment anymore. You are just looking at the absolute value and minus the ideal value. So that's the difference between these two concepts. For the DNLs, you look at the increments compared to the ideal step size. But for the INLs, you just look at the absolute values and minus the ideal absolute values. Can be negative sometimes. You don't have to read it. If you like, you can. But just remember what I just told you, which is going to work perfectly. Look at here. For INLs, do we have any INLs for 0? No? What about INL 1? So look at the absolute value here. So you are using this point, the y value of this point, minus whatever on the ideal curve. And I already labeled that difference for you. So for the subtraction, you are expecting 0.5 LSB. So for INL 1 equals INL 1 equals what?
So we're subtracting
y values, right? So that's the actual value here, right? Because this point is a actual value minus the ideal value, which is a dashed curve. So you are trying to find out the difference between these two. That's INL. Okay. It's called integral nonlinearity because if this one is higher, then if you get more errors, it's gonna accumulate later on. Right? It's looking at you're not looking at the relative increments, but also the final result. So what's INL1? Why -5? No. You're also LSBs. Also LSBs. Keep in mind, even though it's analog output. I know it doesn't confuse you. LSB is a digital value, but we just treat it as it's an LSB analog value. You know what I mean? So you have one LSB as a digital one. It has a corresponding 1-bit increment in the analog. The actual volts depends on your VREF, right? It's like the temperature or the sensor. The last example I introduced last time. So the 1 millivolt, to resolve 1 millivolt, right, for DAC. Then that 1 millivolt can be also called one LSB for the system, for the corresponding analog 1 LSB. Right? So we are just using LSBs because one LSB as a digital one has a corresponding analog 1 LSB as well, right? So here, the unit for both DNLs and NLs are both LSBs, just keep in mind. All right, INL1 is, just use the height of this one minus the height of the ideal value here, which is exactly 0.5 LSB. I think here is one LSB here, right? This is the first step.
Okay,
yeah, that's one LSB. And the actual value here is 1.5 LSB. So you are using, see, INL1 is 0.5 LSB. Yeah, 0.5 LSB.
We can only have 1 or 0.
What do you mean? A 1 or 0?
But we can't go over 1. The LSB, right?
What do you mean by that? You know, depends on how you read it here, right? So for so it uses VL over VREF to, and just this is confusing you. So the corresponding analog output here, which is 1/8, right? So that's the analog 1 LSB over here. You know what I mean? Because 001 is a digital 1 LSB, it's just number 1. 1/8 is a corresponding analog voltage of 1 LSB input. Does that make sense?
So we could, like, if that first point was at like 3/8, we could have a 3 LSB.
It's going to be 2 LSB INL. Because you are supposed to have a 1 LSB, so the dashed curve is the ideal curve, right? So for one input, you are supposed to get this, ideally. But however, it was here, for example, it jumps to here, then your INL1 becomes 2 LSB. Make sense? It can be more than 1 LSB because it can be anywhere, depends on the design. Let's look at more examples. What about this one? 0, and right on the curve, the ideal curve, no problem. What about this one? 0.5. This. Yeah. It's right. It already shows you the difference. So you don't have to do the subtraction yourself. This one. So now let's take a look at it. So this is INL what? INL5 is what? Negative 0.75 LSB, right? Okay, so that was correct. So your calculation was correct. And for INL 2, 4, 6, 7, these are zeros. 2, 0, 4, 0, 6, 0, 7, 0. Okay, just got this sorted out. And then a couple, one example which you'll see on the home assignment. After this one, you should be able to finish it and turn it in on Friday. So this whole R2R ladder is one type of DAC, very simple version of it. DAC. So here's a 3-bit version. Here's VL. R2R means we have 2K here, then so 2K, 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 and 1K here. And these are the digital outputs, D0, D1, D2. That's a DAC. And we use this R2R ladder in the ADC we taped out last senior sum, in the last senior sum. It consumes a lot of power because of the resistors constantly conducting static currents. So that's why it's not a really ideal design. We're trying to replace it with a C2C type of the DAC. So now you can understand why we have to cover Thevenins and superposition in the first week, because this is how you analyze the circuit. And we know that this D0 is LSB, here's the MSB, and why? Why this works as a DAC? Here's a question. So these are the digital inputs. If you put everything in one chip, it becomes a DAC. Right? You got digital inputs, you got analog output. And why is that? Why that works that way? So let's do superposition. And you have to imagine that, because these are voltages, right? These can be 0, 1s. So digital logic 1 is just if you're using a 5 volts logic, it's going to be VDD, just 5 volts. So these digital pins, you can treat them as power supplies, as voltage source. So if I replace it with voltage sources, it becomes something like, a voltage source, a voltage source, a voltage source. All right, I can put 5 volts there, I can put 0 volts here. So if we only have D0, for example, the input becomes, I already told you this is MSB, this is LSB. So if I only have one LSB turned on, it becomes 001. So which is 1, what are zeros and which one is 1? If I only turn on the one LSB here. Yeah, this is 5 volts and all the other two are grounded. It's like a superposition, right? So V1, for example, is the V1, V2, V3. So V1 only, it's going to happen. The circuit becomes grounded, right? Here's VO, 1K, 2K, 2K, 1K, 2K, 2K, and 5 volts. If the input of the DAC is 001, it becomes this. And now let's look at what is VO in this situation. How do you look at this circuit? I know I drew it in a different way as what we usually do. Okay, so here's the voltage source. Okay, if we look at the circuit this way, you got a voltage source, you got a resistor right after the voltage source, and you have a resistor grounded. This is like a voltage divider circuit. And then you have a load. Here's a load. The entire thing here is a load. And this circuit becomes, if we switch this one to the bottom, and this is output network, right? 5 volts, 2K, 2K, right? Just switch it, rotate it here, right? That's how I did it. And then starting from the output, I'm treating this point as the output of this network. And here's ground, and here's ground. So it was like output node, okay? Even though the entire thing, they must have grounds here, and whatever VO has to be referenced to the ground. So everything here is being treated as a load, and when I'm doing Thevenin's equivalent, I just removed this guy from the circuit. So it becomes this. So just like whatever here, I just take it away. And now this is here, okay? So what's the equivalent voltage? I'm looking at this node. What's the equivalent voltage? So I'm trying to find out RTH and VTH. So what's VTH here? And what is RTH if you look backwards? If you short this guy, right? So what is RTH? What is RTH? So when you are doing RTH, you short here, right? And you look backwards. So what is parallel resistors, right? What's the resistance, which is RTH? Yeah. What is VTH? Yeah, it's voltage divider. So you can replace this guy as what? Yeah, something equivalent. So it's going to be 2.5 volts. Just replace whatever here, right? It's going to be 2.5 volts with a 1K resistor. And then just plug this back in here. And then followed by another 1K resistor, which is this guy. And then the 2K going up. And then the 1K. And then the 2K going up. Just 2K, 2K, 1K. Here's still the final V out. So let's label this as VDD over 2. What about that? VDD is 5 volts, for example. So this is VDD over 2, which is 2.5 volts. Okay, and then I replace whatever here with the Thevenin equivalent, which is this guy. And then I plug this in here. So it's followed by 1K, and then 2K, and then 1K and 2K. Is there anything changed? Still the same circuit. What's next? You combine these two as one 2K resistor. Okay? And then it becomes, if you switch this to the top, it becomes this. Just rotate it. It's not going to change anything. Let me show you do that. You don't have to rotate it. I mean, I was just trying to make it look easier. But anyway, let's don't rotate it. You got a VDD over 2 here, and a 2K resistor here, and 2K resistor here. Okay, and then you treat whatever here as the power source, and this guy as a load, and then it becomes what's the equivalent circuit here? You know, which is Yeah. So 2K here, 2K here, and this is VDD over 2, right? Just want to find out, this is the output node. Just want to find out what's the equivalent circuit here. Ground, ground. Why not just put it here? Right? Same circuit. What's the equivalent circuit here? VDD over 4. With 1K. Then plug this back in here. And you're getting that's VDD over 4. That's 1K. And followed by 1K, which is this one. And going up is 2K. And this is the final V out. And these two combined, you are getting a 2K resistor. And the whole circuit becomes, here's VO, 2K, 2K, VDD over 4. So what is final V out? Yeah. And now let's take a look at it. How many bits do I have for this deck? 3 bit. How many combinations I can have? What's the smallest? What's 1 OSB voltage output? VDD over what? Yeah. And now let's see if it's VDD over A. So it makes sense whenever this one applies to the circuit, it contributes 1 OSB to V out. Make sense? It's not a circuit 1 issue if you haven't been in circuit 1. I mean, a lot of people in circuit 1, they couldn't even get here.
I understand this.
Yeah, yeah.
This is starting to make sense.
Yeah, so.
Could I stay here and configure that all out on my own? No, but once you've explained it, yeah. I understand. Cool.
Yeah.
I think I just need more practice.
I think I highly recommend you really work on some Thevenins and superposition. I think you have done a little bit, right, by following the labs. Yeah, very little. But just work on the problem for what they did in circuit 1 in my class. This was the same thing. They just work on. I think that was just one assignment, just one assignment, turning in, done.
Yeah.
So didn't miss too much information. I think you are definitely eligible for being in this class. If you would like to do that, I will give you some time to work on that Thevenin assignment and turn it in. I'll give you some feedback on that. So you'll be more confident in Thevenin's theory in the future. But anyway, so the D0 contribute 1 LSB here. So what about D1? If you put them all together, you don't like, it's a lot of sources. You have to use mesh and nodes. Sometimes it's confusing people because we are doing DAC. It's a DAC. It's good to look at each one's contribution, and because we are looking at only one voltage, so you can definitely superimpose all the contributions to the final V out. So D0 contributes VDD over A. Okay, and if D1 contributes VDD over 4, and D2 is going to contribute VDD over 2, and you add them together, it's going to be the final V out. But now for if I only input 001, what are the contributions from these 2 bits? Nothing. So if you have 001 as a digital input, what's the analog output you are expecting? Of VDD, which is correct. We just did the calculation. It's exactly that value. Okay. So what about V2 only? What about V2 only? Or D2 only? Then the circuit looks like this. Because V2 only, so the D0 has to be shorted to 0 because it's going to be 0, 1, 0, right? D2 only. It becomes 0, 1, 0, right? So only the middle one is on, but all the others are off. Only here has a voltage source. And this one is grounded as well. And here's the final VL. It's 2K, 1K, 2K, 1K, 2K, 2K. All right. How to simplify this circuit? Where to get started? Only the middle one is on. It's 5 volts or VDD. What is that? Yeah, just 1 ohm resistor. 1K ohm resistor. And then these two are in series. Yeah, so this two becomes a 2K resistor, right? So 2K resistor shorted to here. You do Thevenin's, okay? And so you can convert this network over to VD over 2, right? And then 1K. That's a 70 equivalent being shorted to here, right? Then it becomes VDD over 2. And you get 1K, 1K is 2K. And 2K. Here's VO. So what is VO? Yeah. Does that make sense?
Yeah.
But how to calculate it in DAC? Let's verify it. It's still a 3-bit DAC. And when the input is like that, the output is going to be VD over 4. Is that correct? So that's the input. How to calculate the final output for the DAC times what? Which equals V out. That's how you calculate it, right? Which is 2 times VDD over what? That's the final output. Now you see why superposition is so sweet to use in here. So what about V3 only or D3 only? Ground, because these are not on, these are both off. This is only voltage that is on. V out, that's 2K, 2K, 1K, 1K, 2K, 2K. Now how you deal with it? How to do that? And combine these two, the 2K and 2K parallel with this 2K. So the whole thing here is just 1K resistor. And then 2K. So what is this? VL. If you only have this one on, it contributes VD over 2, this much voltage to VL. So if you have all of them on, what's the output? What's the final output? which theory you want to use. No, I mean which theory you want to use when you have all of them on superposition, right? So if you have input, for example, the digital input. If the digital input is 111, right? VL equals this plus this plus, which is, that's the largest input it can get for the DAC. Remember what's the full scale output for the DAC? VREF, right? Here VDD is VREF, which is correct. So VREF times that's what we got last time, right? Is that the same thing here? Yes. So it's VDD times 8 minus 1 over 8.